Right, the last learning objective of this section is the squiz theorem. So let's try to go over what squiz theorem says. All right, let's say like you're going to find the limit of f as x approaches c. Let's say like the graph of f is this black curve over there, right? And let's say like f is not defined at c, so you can't use the direct substitution. But if you can show that f can be squeezed in between two functions h and g, and graph-wise you can see that the black graph is in between the blue and purple or pink graphs, especially in the neighborhood of c. So the limit of f can be found by looking at the outer limits, in other words, the limits of the outer functions. And here's the official description of the squeeze theorem. You see that h is less than f, and f is less than or equal to g. So in other words, f is squeezed in between h and g for all x in an open interval containing the limit point. And it doesn't need to be like c, so the function doesn't need to be defined at c. So if the outer limits are the same, which is in this case capital L, then the limit of the middle function, which is f, has to be exactly equal to L. So going back here, if the limit of h and g exist, and let's say like if it is the value L here, whatever that value is, okay, so the limit of the middle function is exactly equal to L. Okay, so it's called the squiz theorem. A perfect example of this is the function x times sine 1 over x. And I'm going to show you a Desmos animation to see why this limit is easily calculated by looking at two simple functions. Right, the blue graph here is the graph of sine 1 over x. And the orange and the pink ones are the graphs of x and negative x, so y equals x, just one line, so this orange one, and the other one is y equals negative x, that's another line, that's the purple line. As you see that the blue graph is squeezed in between two lines, especially around the origin where the limit point is. As you see that the function values are squeezed to 0. So this tells us that since the limits of the lines could be easily calculated by direct substitution, we can get that limit to be exactly equal to 0 because the blue guys get closer to origin. All right, here is the inequality that we have. So the outer functions are h and g. So let's use the right notation here. So h and g. So let's go back here. So this guy is h of x. This guy is g of x. Obviously, this is the given function. So the limit of h as x approaches 0 is just minus 0 by direct substitution, which is 0. And the limit of g of x, which is the limit of just x by direct substitution, it's 0. So that forces the middle function having the limit exactly equal to 0 by the sandwich theorem. So I can go ahead and then conclude that this limit is exactly equal to 0. Limit of this function is exactly equal to 0. Right, we're going to close this section by providing you this three special limits, and you can also prove those limits by using the squeeze theorem, but you could just use these results and know these results, essentially, put them in your formula card. So you have sine x over x that has the limit 1 at x equals 0. You have 1 minus cosine x over x, and the limit of that as x approaches 0 is equal to 0. Okay, and there's another special limit, 1 plus x to the power of 1 over x, and the limit of that as x approaches 0 is the special number e. In some contexts, you can use the definition of e as this limit. All right, so as I said, you are going to be able to use those known limits to evaluate the limits of other functions. And here's an example. So we're going to find the limit of tangent x over x as x approaches 0, and this function is a rational function, but that involves a trig function, tan x. And if you use the direct substitution, you will see that tan 0 over 0 is just 0 over 0. That's an indeterminate form. Okay? To be able to calculate this limit, I'm going to use one of the known limits in the last result that I have shown you. Okay, so and to be able to do that, we have to use the definition of tangent x. Well, tangent x, first of all, is sine x over cosine x. So I'm going to replace tan x in that limit by sine x over cosine x. Okay, all divided by x. Okay, using algebra here, we can just say that this limit is equal to sine x over x times cosine x. Okay, so now I'm going to try to isolate sine x over x from 1 over cosine x because I know the limit of sine x over x as x approaches 0 in the previous slide, right? That was 1. So how do you separate sine x over x from that cosine x over there? I'm going to use the property that I mentioned earlier. The limit of the product is the product of the limits. So I'm going to divide this limit into the product of the limit of sine x over x and the limit of 1 over cosine x. All right, so as I said, I know that this limit of sine x over x is 1 from the previous slide, and 1 over cosine x has the limit by direct substitution, 1 over cosine 0, but cosine 0 is equal to 1, so it's 1 over 1. So we conclude here that this limit is exactly equal to 1, and then so is this limit. And what did I use here? I used the known limit of sine x over x at 0. That's 1. And another property that I used here is the limit property, that the limit of the product is the product of the limits. And you can graph the function tan x over x around 0, and you will see that this function is not defined at 0, so you have a punch over there. But you will see that this limit is exactly equal to 1 because the function values approach 1. All right, I think we mentioned about all 5 learning objectives. To practice each of those techniques, please go ahead and start the video recitations that you can find in Blackboard, and you will have a lot of exercises practicing all of these techniques. So thanks for watching. I'll see you in another video. Bye.